Thank you, and thanks for the invitation to speak from the comfort of my room. It would have been nice to be in person. On the other hand, at least our carbon footprint is very diminished by this, so that's nice. All right, so I'm going to talk about, as you said, scattering of inertia-gravity waves by turbulence. And this is joint work with Hossein Kafiabat, who's a colleague at Edinburgh, Miles Sava, who's a former PhD student, and Michael Cox, who's a current PhD student and who's in attendance today. So just a bit of background first. Something you've been hearing a lot, I suppose, in the last few days, is that there are two types of motion in the atmosphere and the ocean. So I'll be talking largely from a theoretical perspective, and so I won't distinguish very much for the moment the atmosphere and the ocean. So there are two types of motion with well-separated time scales. That is, if we consider just mid-latitude dynamics, okay, so away from the equatorial region. The two types of motion are first the balance motion, which is this large-scale, slow motion evolving on time scales of the order of days or more, right? So this is really for the atmosphere, the weather, changing not very much from one day to the next, involving cyclone and anticyclones traveling slowly across the globe. That's the slow part of the motion. Then there is the fast part, which is made of waves, internal waves, or in fact more precisely inertia-gravity waves. And so yesterday, for instance, Eric Dazzaro talked about them at length in the ocean. So these are fast oscillations with timescales less than 1 day, and very often much less than 1 day, right, from minutes to hours. If we think about the ocean, they're generated by a combination of effects, so topography at the bottom, the wind blowing at the surface. In the atmosphere, they're generated by convection. There's also tides, both in the atmosphere at high altitude and in the ocean. And also something I was interested a lot in, there's also spontaneous emission, which is the emission by the balance motion itself. So when they evolve, those kind of large cyclones, anticyclones generate also fast waves. And just to get a bit of a visualization, I like to show this picture by Dazzaro et al. This is what they obtained by taking a ship and dropping a bunch of buoys at the surface after a heavy storm in the ocean. What you see here are the trajectories of those buoys drifting naturally, and you see this combination of a slow drift and those oscillations which are marks of inertia-gravity waves, or here just purely inertial waves. Okay, so when you see this, it is really a kind of textbook example of a two-time scale system, right, where you have this superposition of a slow motion and fast motion. And one of the things you want to do, for instance, is to average, right, so kind of to remove those fast oscillations. Another perspective on this is by just measuring, say, velocities at a given spot, is in this case, again, in the ocean, and then plotting the frequency spectrum, so energy as a function of frequency. And what you get in many places of the ocean is a picture like this, okay, where you see that this is a log plot, of course. So these are the low frequencies which dominate largely the spectrum. So there's a lot of power under this area, much more than you might imagine, just because of the log coordinates. And then there is also some energy, quite a bit in fact, in the range of frequencies available to inertia-gravity waves, which are frequencies between, as we'll see in a second, between the Coriolis frequency and then the buoyancy frequency. Okay, so you get those peaks, typically a strong peak at the inertial frequency, so this is the lowest frequency available to inertia-gravity waves. And then depending on the location, you get also tidal peaks. And all that stops to lead to a continuum, which is what was discussed yesterday by Eric Dazzaro. Right, so what can we say about those two types of motion? Just to refresh ourselves, the balance motion is large-scale slow, and the upshot of that is that it's dominated by Coriolis force and will be in geostrophic balance, or approximately in geostrophic balance. So that's this balance between the Coriolis force and the pressure gradient. So that's what controls this, the horizontal velocities, if you like. And then in the vertical, the balance is simply hydrostatic, right? So the pressure at a given point is just the weight of the liquid or the fluid on top of it. Those two balances imply that the motion is almost or horizontal. So to a good approximation, you can ignore the vertical velocity, and it's non-divergent in the horizontal. So you can introduce a stream function and treat the fluid as being two-dimensional, except for the fact that there is a z dependence, right? So people like to talk about layer-wise two-dimensional, so you really have kind of motion sort of pancake-like with some coupling between different depths, between different altitudes. So that's the structure of balanced motion. Inertia-gravity waves behave rather differently. So first, I mean, why are they there? Well, it's because of this combination of the Coriolis frequency and the buoyancy forces, the fact that the ocean is on and the atmosphere are on a rotating planet, so that's Coriolis, and also the fact that there is dense fluid at the bottom and lighter fluid at the top, so there is a stratification. So that is what makes those waves exist. And then it's a simple exercise to figure out what the frequency is, and what you find is this frequency sandwiched between the Coriolis frequency and the buoyancy frequency. So typically they are in this order, right? The Coriolis frequency is smaller than the buoyancy frequency. And then the wave frequency is given by this expression, which involves only this theta. This theta is the angle that the wave vector makes with the vertical. Okay, I mean, many of you will be familiar with this, but it's something to keep in mind, that those waves are really exceptional in the sense that they don't depend on the scale of the waves, they only depend on the direction of propagation. Okay, so this formula just by itself tells you that omega is between those two bounds. And then I emphasize here the time scale separation between the two. Well, that's measured by the Rossby number. That's the canonical small parameter in the atmosphere and the ocean, which is this ratio between the flow time scale. So the flow time scale is going to be L over U, or the balanced motion time scale, I should say. It's going to be L over U because balanced motion is typically of an advective nature. It's a motion which kind of moves stuff, fluid, about with a certain velocity over a certain length scale. So L over U is the time scale of that motion. And then the time scale of the waves, which is bounded by the inverse of the Coriolis frequency. Okay, so it's a natural time scale separation. It's a small parameter of the order of 0.1 in the atmosphere and maybe 10 to the minus 2 in the ocean. So, I mean, my interest has always been in the interaction between those two types of motion. And here specifically, we've asked the question, if we have some kind of complicated balanced motion, what is the impact that it has on wave propagation? And by complicated, we mean really turbulence, right? So balanced motion is fully nonlinear, and well, its typical behavior is to be turbulent in a sense which is of geostrophic turbulence, so that this turbulence where the motion is always in geostrophic balance, which means that it's layer-wise two-dimensional turbulence. So what is the effect this has on waves? And so I just want to show this movie, which I should start from the beginning. Here it is. So what I'm showing here is a simulation of a cube, or a triple-periodic cube of fluid governed by the Vanneste equations with rotation. I'm showing two horizontal slices. So one is a horizontal slice showing the vertical vorticity, and that really sort of filters out the waves to a very good accuracy to leave what is just the balanced motion. And we've initialized the simulation so that the balanced motion is a kind of nice, mature, turbulent state. So a bunch of vortices which are going to evolve and merge and create filaments, have their own lives. And on top of that, we've initialized just a pure plane wave. And we see this plane wave by showing a horizontal plane again of the vertical velocity. So because the balanced motion has essentially no vertical velocity, if you plot the vertical velocity, what you see is largely just the gravity waves. So let's just, I mean, you can imagine that those waves propagating in this complicated flow are going to be strongly affected, and they are, right? So this is what the movie shows. The waves, well, the wave which was a plane wave starts to deform, right? So you see both that the crest start to deform, and also the amplitude start to become highly non-homogeneous. And then if you let this go, you quickly generate very fine scales in the wave field. You lose any sense of direction, in the sense that I started with a plane wave with a favored direction, right, traveling from left to right. Now we have a field which is essentially isotropic. There is no detectable preferred direction. And so it goes to smaller and smaller scales. So this is the scattering of gravity waves by this turbulent flow, this geostrophic turbulence. We want to quantify this. Any questions at this point when my introduction is over? No? Okay. So, as I just said, the aim is to predict this scattering resulting from the interaction of the waves with this turbulence. So what we're going to do is to take a rather mathematical approach and regard this as an instance of wave propagation in a random field. Okay, so we're going to model the turbulence, and here the turbulence is completely determined by just one function, the stream function, since we're assuming this is a geostrophically balanced turbulent field. And we take this function as a given random field, okay, with known property. And for the moment, we make it time independent. The idea here is that the speed of propagation of the waves are much higher than the kind of typical timescale of evolution of the turbulent flow. So the waves propagate in this flow almost as though it was frozen. Okay, this is not quite true, and I'll say a word at the end about relaxing this. We're going to assume linear wave dynamics, so we're going to be interested only in what the flow does to the waves. We're not going to be interested in the wave-wave interactions, something which is thought to control part of the wave spectrum at small scales, as discussed yesterday. We're going to here just completely ignore this by linearizing the problem. So waves do not interact between themselves; they only interact with the flow. And then, of course, we have this small parameter. We have this Rossby number, which is small. We're going to take advantage of this. And so, as I said, I mean, this is an instance of waves in random media, kind of classical problem. And we've used a technique in this paper by Ridzik, Keller, and Papanicolaou, which I think is a very, very nice paper, which lays out how to do this systematically. So there's a question in the chat which asks, what is the range of the simulation x, y, and time? So, I mean, x, y, the size is just 2 pi by 2 pi, right? So this is a periodic box. So I think the relevant thing, I mean, you've seen the picture. The relevant thing is that, so it's a periodic domain, and so it fits quite a few vortices, right? So the characteristic size of flow is the size of those vortices. It fits 20 of those, so that would be the extent. And then the time scale, that's a good question. So, I mean, the simulation it's a very short time scale in the sense that the vortices don't evolve very much, right? So it's a time scale for the scale of the waves to shrink from the original scale to this kind of soup. Okay, and we'll get back to what that means. But you see that the flow itself, the balanced flow itself, evolves not very much. So it's barely 1 turnover time of this flow. Does that answer the question? Okay. Right. Okay, so I'll be showing 2 types of results, if you like. My mouse is gone. That's unfortunate. There it is. So I'm going to derive 2 models for how the wave amplitude is being modulated by modulated or scattered by those gravity waves, or those inertia-gravity waves. One is a kinetic equation which makes no approximation about the respective scale of the waves and the flow. So you've seen in my simulation that the vortices, at the beginning at least, have a size which is comparable to the wave scales. Okay, that will be captured by this kinetic equation. The kinetic equation is a bit complicated to interpret. When the wave scales get much smaller than the scales of the vortices of the turbulent flow, then you can use a diffusive approximation, which is a kind of reduction of this kinetic equation, which is much easier to interpret. And you've seen in my simulation that it takes a very short time to move into this regime. So even if your waves initially have a scale comparable to that of the vortices, after a short time, they turn into small-scale waves by the scattering. Okay, so a little bit of mathematics. I won't give you the details. It's fairly mechanical if you follow the method of the paper I mentioned. You start by just writing your equations of motion in some kind of symbolic form. So my phi here is a vector containing all the relevant dynamical fields, so velocity, pressure, buoyancy. And, well, I mean, symbolically, pretty much any system can be written in this form. So what do we have here? We have a linear operator. So in the absence of this n term, this would be... So there's a question, is there a forward cascade of energy of the inertia-gravity waves? Yes, that is correct, right? So what we've seen in the animation is that the energy is going to smaller and smaller scales, and that's precisely what I'm going to describe. So we have a linear part. So this is written symbolically. If you look at the spectrum of this operator, what you get are the frequencies of inertia-gravity waves. And then there is a nonlinear part, which is not really nonlinear. What it is the effect of the flow acting on the waves, right? So it's still linear because we've linearized our equations. There is no wave-wave interactions. But it depends on the flow, and so it depends on spatial scales. It depends on space, potentially on time, but not in the first instance. And then there is some kind of funny scaling. Okay, this is essentially saying, okay, the flow is weak. This is a small Rossby number assumption, so the time scale of the flow, which is also the strength of the flow in this geostrophic approximation. The strength of the flow is small compared to the restoring force of the waves. And okay, so don't be alarmed. So this is just saying that the scale of the flow is the same as the scale of the waves. We're going to be interested in what's happening over many wavelengths, right? We're trying to describe the field, not we're going to have a phase average description of the field. What we want is to know what is the amplitude of the waves rather than precisely where the crest and the troughs are, which is going to be a random thing, right? So we want to focus on the deterministic part, which is the wave amplitude. Okay, so then you can ask, how do I study waves in this background which depends on space? Because what you want to do is to describe waves in the usual way, that is in sort of Fourier terms, because waves naturally are expressed in terms of their wave numbers. On the other hand, there is a spatial dependence of the flow and hence of the wave system. So how do I cope with both spatial and wave number dependence? And one answer, which is very clean and simple, is to use this Wigner matrix, which is, you can think of it as some kind of local Fourier transform or local spectrum of the wave. So what you do is that you take all your fields, you look at them at two positions, x plus epsilon y over 2 and x minus epsilon 1 over 2. So you look at two positions shifted by a small amount, epsilon y, and then you make a Fourier transform with respect to the small difference. Okay, so what you get now is a matrix, so it contains all information about all the fields, both in space and in wave number. Okay, so you now have a description in phase space, which allows you to capture the waves in the usual sense of waves having wave numbers, but also capturing some variations in space. And I mean, this is some simple transform, if you like, of phi. So you can write down an equation for this Wigner matrix. And then there's a small parameter. You can just sort of turn the crank, expand your Wigner transform in power series of the small parameter, and do some kind of multiple scale, because there are two scales involved. One is the scale of the waves, which is also the scale of the flow. The other scale is a large scale over which the wave energies or the wave actions are going to be modulated. Yes, so Victor makes a comment that there are things along those lines in the 80s. That is correct. I mean, there are also papers by Müller along those lines. I don't have the time to tell you how this is different, but I mean, I think largely in the 80s, for computational restrictions, they very much focused on one-dimensional propagation, so in the vertical, which somehow, I mean, interesting aspects are being lost. All right, so you turn this kind of perturbative crank, what do you find? Well, to leading order, you find that your Wigner transform, Wigner function, matrix, is given by some amplitude, just a number depending on position in phase space, so spatial position and wave number, and then times a matrix made up of those vectors B. They are just the polarization relation. So these are those vectors which encode the relationship between various components U, V, W, P, rho of the gravity wave fields, of the wave fields. Okay, so when you have a wave, you have always these relations between the different components of the fields. They are encoded in this B. Okay, so really the interesting information here in this A, this amplitude, which you can think of as a wave number resolving energy density. Okay, so it tells you how much energy or how much action. I want to go into the details of the difference really. It's essentially equivalent for a problem. So it's the energy at location X and wave number K. You continue turning this crank, and what you get at the next order is an evolution equation for this amplitude. And it's not terribly surprising, it's this kinetic equation. Okay, so let's look at what it says. It, on the left-hand side, you have really the classical action equation for any wave system. So there will be change in the action density as a result of transport by the group velocity, right? This guy here, gradient of frequency with respect to wave vector, that's the group velocity. So this is transport in physical space due to the group velocity. And then this is refraction. This is transport in the k direction of the phase space. So this is change in wave vector caused by the spatial variation of the frequency. So this is the homogeneity of the system potentially. The omega here is the intrinsic frequency, so the effect of the flow is not there. The flow effect has been completely turned into this right-hand side, which is a scattering operator. So what this tells you is that the action or the energy at a certain k is going to be to evolve because it receives action from different wave numbers, k prime, and the rate of transfer is encoded into this sigma, this cross-section. Okay, so sigma tells you how much action is transferred from wave vector k prime to k as a result of the scattering. And then the big sigma is a total scattering cross-section, which is just the integral over k prime of this sigma. So this is how much action leaves wave number k because some energy from wave number k is being scattered to other wave numbers k prime. Okay, so this is kind of a standard equation, which is what you expect. The question is, what is this scattering cross-section? Different wave systems will have different cross-sections, and so in our case, this cross-section will depend on the flow statistics. So what is it like? Well, here it is. I mean, I'm not giving you the full formula, which is pretty ugly looking. I'm just saying it. I'm just extracting the two important ingredients. The first one is this dependence on this E, which is the energy spectrum of the turbulent field. Okay, so the only property of the turbulent field which matters, it's in fact the kinetic energy spectrum. It's not so surprising it's the only property because really this flow is determined just by one field, the stream function. Okay, so one statistics, if you like, of the flow should be enough. Things work on in such a way that only the energy spectrum, so the correlation function of this turbulent field matters. Okay, so high order statistics are irrelevant, so we don't have to assume that it's Gaussian. It's only the spectrum which comes into play. And then the second ingredient is this delta function, which tells you that exchanges of energy will be restricted between waves which have the same frequency. Okay, so no exchange unless k is equal to k prime, or at least omega of k is equal to omega of k prime. So yeah, omega of k is equal to omega of k prime, so waves which have the same intrinsic frequency. So this is not surprising really, because if you look into the details, what's happening is that the interactions which we are represented here are triadic interactions involving, so a triad is an interaction between three different sort of wave modes or modes in the system. The three involved here are two inertia-gravity waves, and then there is a flow. Okay, this is what some people refer to as catalytic interaction, because it turns out that this has very little effect on the flow. So the flow just affects the waves, but there is no feedback of the waves on the flow. So we have this triad where we have one inertia-gravity wave interacting with the flow to create or modify another inertia-gravity wave. For those interactions to be effective, they need to be resonant, which means that the frequencies have to match. And so we have the frequency of a wave, omega. The flow frequency is here strictly zero. We've taken it to be time independent. And so it's not a difficult calculation to see that this receiving inertia-gravity wave has to have the same frequency. Okay, and at what level is trivial? I mean, all we're saying is that if we have a time-independent flow, waves are not going to change their frequency. There's nothing to change their frequency, right? So the prediction, if you like, is that all the transfers will be restricted between waves which have a given frequency. Wave with a given frequency in wave number space correspond to wave numbers sitting on a cone, right? Because the dispersion relation of those waves is such that the frequency depends only on the angle of the wave vector to the vertical. Having a given frequency means having a given angle for the wave vector to the vertical. That means sitting on a cone. So here is this cone. So this is wave number space, kx, ky, kz, scaled in a kind of natural way. And this is the result of some simulation where we started with, as I recall, just one plane wave with a given spatial structure, hence a given frequency. And then later on, we put dots where the energy, where we find energy, significant energy in the Fourier transform of a wave field. And you see that this energy is completely confined to the cone, right? I mean, it appears on rings, and this has to do with the discretization. But apart from some weak amplitude outliers, which arise because this is a full simulation with nonlinear interactions, much of the energy is confined to this constant frequency cone. And so, I mean, this is the same kind of picture where this is exactly the simulation I showed you at the beginning, the movie. So the top panels correspond to what we saw in the movie, the wave field, the vertical velocity corresponds to the wave field being kind of deformed, and that's the Fourier perspective. So that's the wave number space perspective, where you see we start with a single point, single plane wave. Energy spreads in angle. That's this business of the preferred direction sort of being lost in the evolution. And then energy also tends to go to small and smaller scales. So J asks whether there's forward cascade of energy. Well, yes, there is, right? So energy goes to larger and larger k, so small and smaller scales. But it does so while staying on this cone. And one of the reasons there is this cascade towards small scales is that there is much more space on this cone at large k than there is at small k, right? So somehow the geometry of this cone is very important to decide what will be the spontaneous behavior of the system. There's an infinite amount of space available for large k in the cone. So the fact that that this constant frequency surface is not compact, right? It goes all the way to infinity is very important for what I'm going to talk about. All right, so all the information is contained in the scattering cross-section, okay? Really, the scattering cross-section is best thought of as a matrix because a cone has two, the technical term I learned is called a nap, okay? A cone has two naps. So there are two bits, the top bit and the lower bit, the two naps. And really, you have to think about interactions between waves lying on the same nap of the cone and interaction between waves lying on opposite naps of the cone. And there's a hint here that not much happens for waves sitting on opposite naps of the cone, in the sense that the energy, by and large, stays on the nap where it started. Okay, so what we do is that we split the energy into two, so the energy density, my A, into two bits, the bit which corresponds to the upper nap. So these are waves propagating up, I should say. The lower nap corresponds to waves propagating down. And then you can write a coupled system of equations. I've here removed all the business of advection by group velocity and refraction to concentrate just on the scattering. Now you have this 2x2 tensor, which tells you about the exchange of energies for waves between various wave numbers sitting on different naps. So the diagonal elements will correspond to interaction on the same nap, and the off-diagonal element to interactions between the different naps. And so you can plot those guys. Okay, so those plots are a bit difficult to understand. So what they show is one of the components of this tensor. We fixed the sort of source, or receiving, maybe I should say, wave vector. Okay, so it's between 0 and 1 here. So that's the 0 and 1, I guess. That's the sorry, between 0 and 1, yes, here. That's the oops, should have clicked. That's the tip of the receiving wave number, and we ask for all the other wave numbers sitting on this plane. So you can think of this as a projection of the cone on the horizontal plane. How much is the transfer rate? And you see things like, so there is a very white line here, which is saying that waves do not exchange energy with other waves which propagate in exactly the same direction. And then there are those lobes, which are maxima of the energy transfer. And so what you learn is that the maximum energy transfer happens for waves which make a certain angle, okay, between 0 and pi/4 with the receiving wave. And you can do this for both the interaction between waves on the same nap and then of opposite naps. And what you find is that, I mean, if you look at those numbers, okay, in some sense, there's a bit of a subtlety here, but the exchanges are much weaker across naps than on the same nap. And you can do this for different receiving wave and different parameters. So one of the things which emerges, for instance, is that even though the exchanges tend to be weak between naps, in the long time limit, there will be an equilibration. Okay, so the equipartition of energy, all the waves will have the same, waves propagating up and down will have the same energy. Okay, so this is a bit complicated to interpret. What is much simpler to interpret is the diffusion equation that we get when we make the assumption that the wave scales, so the wave numbers, are much larger than the wave numbers of the flow. So this is to say that we're dealing with waves which have a scale which is much shorter than the flow scale. And as I said, I mean, this is happening very fast in practice. So in that case, my scattering operator, this integral operator, can be reduced to just this diffusion operator. Okay, and here an expression, so it's fairly straightforward. For any wave vector here of the wave, it gives you what is the corresponding diffusion coefficient, and it depends on the correlation function of the velocity field. So it depends on the wave spectrum, right? So the correlation function and the spectrum are Fourier transforms of one another. So this is not new. So this was derived first by McComas and Brotherton for wave-wave interactions. So they use this using what for me is the flow. Their flow was actually large-scale, low-frequency inertia-gravity waves. Okay, whereas my flow is really balanced flow. So the formula is the same, but the kind of look of this correlation function or tensor is going to be different because we're talking about different flows. And in particular, the fact that I have a time-independent flow, or very slow, which means that the energy transfers are restricted on this constant frequency cone, translates into the fact that this diffusivity tensor has the group velocity in its kernel. Okay, so if you think about this means that the transfers there will be no transfer across the cone, right? Because the group velocity is a gradient of the frequency, so that gradient is orthogonal to the constant frequency surfaces, right? So the gradient is always orthogonal to the level surfaces. So this is just a statement that there is no diffusion across this cone. So we have two predictions, rather kind of detailed prediction about what is happening, what should be happening in simulations, for instance, and hopefully also in the atmosphere and the ocean. We can test this, maybe not by going to the atmosphere and the ocean, but at least numerically. So we've run a 3D Boussinesq code, I mean, of the type used for the simulations I showed. So some details, I mean, it's a spectral code with a fairly respectable resolution. We run this at a smallish Rossby number. So that tells you about the strength of the flow initially, with a ratio n over f, which is, I mean, a bit on the low side, but pretty reasonable. I mean, it's very much like in the simulation that I've shown. So we initialize a nice QG flow. We initialize the waves. The only difference is that I started my flow with just a plane wave. I don't want to discuss too much the phenomenon of this plane wave losing its preferred direction and become isotropic. Okay, so to avoid this and have a simpler system, we start with a wave field which is already isotropic. Okay, so that corresponds to, instead of exciting one point in Fourier space, we excite one ring. Okay, so what I'm showing now here are the results of two simulations with two different ratios between the flow scale, which is the same in both simulations, and the initial wave scale. So in the first simulation, the wave scale is much shorter, so we are in this regime where diffusion applies, so we have this diffusion in wave number space. I should have stressed this, right? It is all in wave number space, so it's a diffusion in wave number space. And then below, it's a simulation where the wave scales are the same as the flow scale. So at least initially, this diffusion approximation does not apply, and we have to use the full scattering equation. Okay, so those pictures are not so easy to read. It's this amplitude of the wave energy as a function of wave number. So this is the distance along the cone. The positive distances correspond to the upper cone, the upper nap of the cone. The negative distances, a counterintuitive notion, correspond to the lower nap. Okay, and time goes from top to bottom. So initially, I should say this theory does not work for the very early time. So it's a statistical theory which assumes that waves have had a chance to propagate enough that they have encountered a variety of vortices, say, which reflect the statistics of the flow overall, right? So there's a time over which the results depend on the precise draw, if you like, the precise, in the fine details of the flow. After a while, the wave field depends only on statistics of this flow. So what we do is that when we compare numerical results of the Boussinesq code with what the scattering equation tells us and what the diffusion equation tells us, we do a matching after initial time. Okay, so initially I have three curves. The black curve is the Boussinesq simulation. The red curve, which is not seen because it's completely put by design on the black curve, is the result of the scattering equation, the kinetic equation. And then the blue curve is the result of the diffusion equation. And I didn't say this either. In this diffusion approximation, there is no interaction between the two naps of the cone. Okay, so upward propagating waves will not give rise to any downward propagating waves. It's a kind of standard WKB behavior. So we don't initialize anything on the lower nap of the cone for that simulation. Okay, and so what you see is that as time goes by, we have a very good prediction in this case of both the scattering, the kinetic equation, and the diffusion equation. So this is for a certain frequency of the waves to f. That's for higher frequency. You have this good match. And here downstairs, that's a situation where you don't think that the scattering is well represented by diffusion. You have to use the full kinetic equation, and so it proves. Okay, so if you follow the evolution, you'll find that the black line, the red line rather, which is the prediction of the kinetic equation, is doing rather well, but the blue line is not. Okay, so essentially what happened is that in the early stages, diffusion is not a good approximation, and so that affects the rest of the evolution. Okay, so someone is asking, how is the QG turbulence set up? Yeah, so we start with random initial conditions and then let the system grow spontaneously to a stage where somehow most of the inverse cascade has happened, and then there's only a very slow evolution of the system. So by that stage, because the wave evolution is so fast, we can consider that we have a balanced flow, a QG flow, which is well developed and whose statistics are essentially stationary. The statistics are evolving slowly because the inverse cascade continues, and ultimately there'll be some pile-up of energy at the larger scales. But because we're interested in a rather short time, because we are really interested in the time scale of the wave cascade, we can get away with that. Okay, right. So this was an initial value problem, which is a kind of tough problem. Now let's look at the simpler one, which is a force problem. And the question is there can we predict some equilibrium spectrum? So if we force the wave field at a certain wave number, we've seen that we have this cascade where wave energy is going to start filling up this cone, which corresponds to a cascade to smaller and smaller scales. Is there a stationary spectrum that can be predicted? So it's natural to write things in terms of this E, which is the one-dimensional spectrum. So we ignore all the angular dependence. We are in a situation where there is complete homogeneity in angle. So we look at this E, but that's just the action. And in the diffusion approximation, it satisfies just a 1D diffusion equation. Okay, so all these calculations boil down to actually fixing just one number, is Q. We have this diffusivity which depends on K cube. Okay, so that's, you see a 5 here because we are in spherical geometry, so there's a K square coming from just, if you think about the Laplacian in spherical coordinates, you have a K square, we have a K cube. So K cubed is the diffusivity in wave number space. And so Q is this single number which depends on the flow. So what it is telling you is that if you have different flows, they will have different Qs. They fix the time scale of evolution of the system. They fix the flux of energy, but they don't determine the type of spectrum that you get. Okay, it's because you can scale this Q out by rescaling the time. And now if we look for a stationary solution corresponding to forcing just one wave number, we find just very easily, right, by solving the right-hand side equals 0, that there is a K square spectrum which will be relevant for small wave numbers, and there is a K to the minus 2 which is relevant for large wave numbers. So the prediction is that there is a constant flux solution scaling at K to the minus 2. Okay, and that matches very well what we obtain in simulations. There's a slight shallowing here, perhaps, okay, if you want to be very fine, which maybe has to do with the fact that we ignore wave-wave interactions. For waves of small enough scales, those wave-wave interactions are starting to become relevant. And we like this K to the minus 2 spectrum because it's consistent with observed spectra. Okay, so in the ocean, it is kind of classical to say that in a certain range of scales from, say, hundreds of kilometers down, spectra of the type K to the minus 2 are being observed. For the atmosphere, which is what I'm focusing on here, the tradition is more to say that there's a K to the minus 5/3. Okay, so this is a very famous picture in the field of atmospheric science, which shows spectra as a function of horizontal wave number obtained in the atmosphere near the tropopause by flying aircraft, measuring the flow speeds, and then taking Fourier transforms to get the kinetic energy spectra for. I mean, this is done for the two components, horizontal components of the velocity, and also for the buoyancy. Let's ignore this, but the point is that It's well known that the spectrum sort of makes this knee shape where you have a steep spectrum, which is close to k to the minus 3, which is well explained by quasi-geostrophic dynamics. And then there's this shallowing occurring at something like 500 kilometers, shallowing to something which people typically call minus 5/3 spectrum, without a good explanation as to why this should be minus 5/3. Okay, so recently people, I mean, including Jan Kellius and his collaborators, have done some separation of this data to isolate the balance part from the wave part. Okay, so this is shown here. So I've reproduced a figure from their paper using the data. The black line is a total spectrum, so it shows this steep part at large scales and then this shallowing at smaller scales. And they managed to do this split, which says that, okay, so the red part is the balance part, think of it as the geostrophic part, and the blue part is the wave part, okay? So this suggests very strongly that at small scales, but we're still talking about 500 of kilometers down to maybe 10 kilometers, the spectrum is dominated by inertia-gravity waves. And then the slope that, I mean, they don't discuss slopes, but I do. If you match a slope to this, you find that -2 is a pretty good match. Okay, so one argument is that this spectrum, which was kind of mysterious and still is mysterious, is mostly dominated by inertial gravity waves, and the reason it takes this particular power law is because it's shaped by the interaction of those waves with the geostrophic turbulence, with the balance flow, which is strongly dominant, right? In the ocean, one can make more or less the same, can tell more or less the same story. A difference is that when you get to smallish scales, people strongly believe that wave-wave interactions are critical, and that's how you get the Garrett and Munk spectrum, which was referred to several times yesterday. It's not clear in my mind, actually. Well, two things are not clear in my mind. First, that there is truly an explanation for what the wave-wave interactions will lead to, okay? And what is not also clear is where is the transition. So, I mean, one issue is that people like Eric Lazaro talk a lot in terms of vertical wave number spectrum and frequency spectra. We talk about horizontal spectra. And you can describe very different places in wave number space by doing this, right? So we're talking about what people would have considered in the ocean as being very large scales for gravity waves. All right, so I just wanted to mention one more thing, which is what Michael Cox has been doing in the last few months, and is to relax this approximation, which seems a bit outrageous, to freeze the flow. Okay, so we've treated the flow as being completely time independent so far. And you've seen my simulation that it's not completely crazy in the sense that the evolution of the waves is so fast that maybe it takes place over one turnover time of the flow, but nonetheless it's a bit disturbing, right? So the question is, what is happening if you have non-zero time dependence for this flow? But the flow is still slow, right? Because we still have this small Rossby number. So there's a timescale separation between wave frequencies and flow evolution. So what you get, let me just focus on the diffusive regime, which is what we've done so far. So this regime of small scale waves. What you get is exactly the same diffusion equation as before. But now the diffusivity has the part that we had before, which has a zero, well, which corresponds to no diffusion across the constant frequency cone. So it has this orthogonality with the group velocity. But then there's a time dependent, well, there's a correction associated with the time dependence, which does not have this property. Okay, so there is going to be a weak diffusion across the cone associated with a transient. So I mean, it's completely intuitive, right? Now that the flow has its own frequencies, it's not going to, the wave frequencies are not going to be completely frozen. They're going to be, there's going to be some interaction between waves of different frequencies mediated by the transient in the flow, if you like. this correction to the diffusivity, so this component of the diffusion across the constant frequency cone, depends on the acceleration spectrum. If you think of the energy spectrum in both wave vector, or I mean, yeah, we're talking about the flow, right? So no waves are involved, but this is the Fourier vector, the wave vector of the flow and frequency. The acceleration spectrum is simply this expression, right? So the square of omega corresponds to 2 time derivatives. If you have a flow which is time independent, this is 0, but if the flow is time dependent, it's non-zero. So we get a non-zero diffusion across the cone. So I mean, one reason we looked at this in some details is that there's an argument made by Dong, Buehler, and Smith that this is important in the sense that once you have this diffusion across the cone, maybe the energy could spread into the entire wave number space, and so the constant frequency cone becomes irrelevant. Waves of any frequencies are going to be generated. This is what's happening in 2D, right? So in 2D, the equivalent of the cone, constant frequency cone, is just a circle. A circle is a bounded object, so very quickly energy becomes sort of uniform on this circle, and it kind of spreads across the circle. So you have this kind of 2 time scale system where you have this fast transfer across circles and then slow transfer, fast transfer along circles, and slow transfer across. Things are very different in 3D. This is what we established. Because of this unboundedness of a constant frequency surface, energy is in a one-way street, right? So it just goes to smaller and smaller scales because there's so much room on the cone at large wave number. And so as it does so, there's this kind of small diffusion across the cone, but it doesn't have time to do that much, okay? Because by the time diffusion has acted, the waves have very small scales, okay? It turns out that you can actually solve this problem perturbatively in a very neat way. So if you consider a force situation, so we've just looked at the equilibrium spectrum, where you force a given wave with a given frequency, you can describe how the action distributes itself in wave number, or the energy, it's the same. And this is the angular coordinate. So this coordinate is a rescale angle. So it's an angular distance between the forcing frequency and whichever frequency you're looking at, okay? Because angle is frequency for those waves. Okay, so what he's saying is that we do a kind of boundary layer approach. There is a thin boundary layer around the cone of thickness epsilon, where energy will be confined. Okay, and if you can, it turns out that there's kind of nice result, if you like, 19th century sort of mathematics in terms of Legendre functions. It's completely explicit results, and it says that this energy A and E are more or less the same thing. So if you look at it as a function of k, you get this decay here, which is similar to what we had before. But then you can look at different frequencies, so getting further and further away from the cone. Okay, and so you see that energy is localized near the cone, and we can give a precise description of the shape of the decay. Or you can look at a fixed wave number and look at this distribution. So this is really the kind of profile of energy distribution across the cone. Okay, so you have a localized distribution. As you go further and further along the cone, you get something which is less and less localized. Okay, so at some point really further down, it is the case that waves of all frequencies will be generated, but by that time nonlinear interactions and probably dissipation are going to be important. Okay, so that's my conclusions. So what I've discussed here is a statistical theory for linear gravity waves propagating in a turbulent flow, which is weak in the sense that the Rossby number is small, and it's a turbulent flow of the kind encountered in the atmosphere and the ocean, so a quasi-geostrophic turbulence. What we find is that energy is exchanged between waves of the same frequency, right, through this mechanism of triadic interaction where one of the members of the triad is the flow. So constant frequency modulo the fact that there's a slight kind of change in frequencies, which I've just discussed. We have two two models for it, right? One is the general model, which is a kinetic equation which holds for any wave vector. So the wave scales can be comparable to the flow scales. And then we have this diffusion approximation, which holds for wave scales which are much smaller than the flow scales, but not too large. Okay, so this is a limitation, which is, I should have mentioned this perhaps as well. We are using the fact that the flow is weak compared to the waves. So essentially what we're saying is that the flow velocities are small compared to the groove velocity of the waves. That is not true for very large k, because so that when the waves are small enough, the groove velocity gets small. Okay, so our description is always limited to a range of wave numbers such that the Doppler shift is weak compared to the intrinsic frequency of the waves, or the velocities of the flow are weak compared to the groove velocities of the waves. But in that regime, so we can predict this -2 spectrum, which matches what was seen in observation, and we can describe in fine detail this forward cascade of energy. And also, I mean, I've not talked about this very much, but we can also describe in detail this isotropization, so how waves with a certain preferred direction of propagation lose this preferred direction of propagation. So this last point is that we can account for the frequency. And then just a picture to finish. This is what you get when you apply this. So I've completely focused my discussion here on what's happening in wave number space, and I've assumed homogeneous statistics in physical space. As you've seen, I mean, I have this phase space description where I can cope with both wave number and position. And that's useful if you think about inhomogeneous systems. So this is work which we did earlier, where we looked at how tides were affected in the ocean by the underlying turbulence. So what we have here is we have a wave maker here which makes a plane wave. This plane wave propagates over a turbulent field. And now you see those two effects. I mean, one is as you move along here, you see that the wave becomes less and less, it becomes more and more isotropic. This is the case without vertical shear. As a result, propagation on the cone is happening at constant wave numbers. So you have to look at the intersection between the cone and a plane, a horizontal plane. So you get just a circle. Okay, so we're saying that the waves keep the magnitude of their wave number, but they become isotropic. Okay, so you have this kind of complicated behavior in the full phase space. So we can deal with that too in principle, but it becomes very difficult because you have to solve equations in 6 dimensions in principle. Okay, so I'll stop here.
Thank you very much, Jacques, for this nice talk. So we have still a couple of minutes for questions.
Okay, so Yo is asking, in a time-dependent flow, do waves exchange energy with the balance mode, wave gain or lose energy? So it's a very good question, right? It's a very interesting problem, of course. The answer is yes, but not to the order that we're considering here. Okay, so this catalytic interaction, so this interaction between two wave modes in the flow is very weak in terms of its impact on the flow. So you can think of this in terms of potential vorticity. So the waves do not carry any potential vorticity. So they have a really hard time to modify the flow because they don't change its potential vorticity. So what they do instead is that they modify the advection of the potential vorticity. You know, something which is well described by generalized Lagrangian mean theories. Okay, so you really have to go into this kind of theories to do to study the impact of the waves on the flow.
I have another question in the chat.
Yeah, from Jim Thomas. In the first half, you presented primitive Boussinesq equation simulations. What specific setup prevented the generation of higher frequency wave harmonics? I mean, there's nothing in the setup that prevented the generation of harmonics. In fact, they were generated. Simply, our wave amplitudes were small. I mean, if I go back to my first picture of a cone, I think, whoops, this one, you'll see that there are a few dots of the cones, and if you look at where they sit, they correspond to frequencies which are harmonics. Okay, so it's just a question that we have small wave amplitudes, and as you suggest, our times of integration are very short, right? So there's no time to for wave interactions to do very much. I think they do something at the smaller scales, but this is close to dissipation. This is not something we've looked at in details. So yeah, so what Jim is asking is whether you really need a time-evolving flow to break the single frequency wave cone. So the answer is no, right? So wave interactions will do that for you. Wave interactions will do that in a very specific way, that you're only going to generate harmonics, right? And because of my weak wave amplitudes, they will take forever to do that.
Okay, thank you. Is there a final question?
Is there a final question?
Not yet.
You can also ask orally.
So thank you very much, Jacques. We'll stop for 15 minutes before the next talk by Ganesh. So thank you. And if you want to ask other question directly to Jacques, you are more than welcome.
Of course.
Thank you very much.
For a little bit, yeah. Mm-hmm.